introduced the idea of an oriented triangle, like ABC, with this tilde convention. And he said that this was essentially an ordered set, like ABC, with three elements, each of those elements being an affine point. But with added condition, or the added agreement, that if we rotate the elements, if we take the A and move it to the end, get BCA, or we do it again, take the B and move it to the end, and get CAB, then all of these are going to be equal. So there's an order involved, but there's also an equivalence between these three different kinds of orders. All of them are captured by this notation here of the oriented triangle. Now this is a little bit confusing perhaps from a computer scientist point of view, because we're introducing this convention of saying that this ordered set is really the same as that ordered set. But as ordered sets, if you actually just look at these things, they're obviously not the same as ordered sets. So we're a little bit at odds with our data structure conventions when we try to introduce something like this. So we're going to be a little bit more sophisticated now, and we're going to tackle this problem by introducing another kind of data structure, a cyclically ordered kind of data structure. All right, so we're going to look at the four data structures that we have, and we're going to impose something else that captures the idea that's necessary for us to talk smoothly about oriented triangles, and then later on certain kinds of polygonal splines later in the lecture. So let's introduce a cyclic list first of all, and then a cyclic O-set, or we might call it a C-list or a C-O-set. What we're going to do is we're going to take the idea of a list, there's a list right there, and we're going to put pointed brackets around it. That's going to create a new kind of data structure, which we'll call a cyclic list. And what is it? Well, it's just like a list, but it has this cyclic convention that's exactly the same as what we just talked about. We're going to agree that this cyclic list is the same as this one. What you get when you take the first element and move it around to the back and shuffle everything over. Again, of course, we can do it again, get 4, 2, 1, 1, then we can do it again, get 2, 1, 1, 4. If we do it again, we get 1, 1, 4, 2, back to where we started. So this bracket that we're imposing, in addition to the square brackets, tells us or alerts us that we now have a different kind of data structure. It's very close to being a list, but it's a cyclic list. Okay, it doesn't really have a start and an end like an ordinary list does. It kind of goes around in a circle. Okay, so now we're going to talk about a cyclic O-set. It's also going to be another ordered structure. These are the two ordered structures, list and O-sets. So a cyclic O-set is an O-set with an additional pointed bracket around it. That's going to tell us that we are imposing cyclic equivalence. So the O-set 1, 2, 3, when we put the brackets around it like this, it's the same as the O-set 2, 3, 1, the same as the O-set 3, 1, 2, and instead of calling them O-sets, we'll call them cyclic O-set. That's a cyclic O-set. So this is it's kind of nice, so that we can now identify very easily on the page, that's a new kind of object. That's not a list, it's not a multi-set, it's not a set, it's not an O-set. It's a cyclic list, or it's a cyclic O-set, and we know exactly what that means. So now we can, if we want to, return to our oriented triangles and sort of redefine an oriented triangle in terms of our new notation. An oriented triangle, ABC, is just the cyclic O-set, consisting of 3 affine points. And it's an O-set. There cannot be any repetitions here, right? We're not allowing 2 of these things to be the same. They have to really be 3 distinct points. And more generally, an oriented end-on, A1, A2 up to AN with another tilde on it, can now be rethought or redefined to be the cyclic O-set, A1, A2 up to AN. So it's the O-set with the extra brackets, that means it's a cyclic O-set, or C O-set. And again, this condition requires that each of the AIs appears only once. Because it's an O-set, repetitions are not allowed. So that ensures that every point AI occurs only once. But there's no requirement of convexity or anything like that. These points can go anywhere they like to be. So here's an example: A1, A2, A3, A4, A5, and then back to A1. That would be an example of a picture of the end-on, the oriented end-on, A1, A2, A3, A4, A5 tilde, which is the cyclic O-set, A1, A2, A3, A4, A5. So that's nice terminology that allows us to really think a little bit more broadly or more accurately about what oriented triangles and oriented end-ons are. But oriented triangles and oriented end-ons are great. They are very natural for geometrical investigations, but in calculus we want to broaden the scope. We want to consider more general things. We want to, in fact, drop the requirement that the points cannot be repeated. When we do that, we get more general objects that are in some sense more easy for us to work with, because we don't always have to be checking whether there's repetition or not. Okay, and these are polygonal splines. All right, so let us introduce oriented polygonal splines. These are more general objects than oriented end-ons. They're like oriented end-ons, except that we're being more general in 2 different ways. First of all, repetitions are allowed. We are now going to allow repetitions. And furthermore, closure is not necessary. We are not going to insist that the end-on come back to where it started. So these oriented polygonal splines are going to start at some point, then go there, and then go there, and then go there, and then go there, maybe back to where we already were, and then go over here, and over here, and over here, and over here, and end there. They don't have to end where they started. And repetitions are allowed. So here is the official definition. And we'll introduce this little acronym, OPS, for an oriented polygonal spline. What is it? Here's what it looks like. A1, A2 up to AN with a vector kind of arrow. But notice it's different from the vector arrow that I usually draw. It's an arrow with kind of 2-sided barb, not like a harpoon. Usually draw vectors like this. So this thing is a list of affine points. That's the definition. So A1, A2 up to AN with this arrow. That means this list of affine points. A1, then A2, all the way up to AN. This is a list. You can tell that because it's in square brackets and because there's commas. So repetitions are allowed. And it's ordered. There's a first one, there's a second one, there's a last one. The AIs are, of course, affine points. That is then really a generalization of an end-on, a very flexible kind of thing for us, very useful. And while we're at it, we're going to introduce a particular kind, so the simplest kind of such thing, which isn't trivial, is an oriented edge. Well, we only have 2 affine points, A1 and A2. And so we have an oriented edge, A1, A2, which is just the list A1, comma A2, end of list. And we'll call that an oriented edge. So that's a OPS, or oriented polygonal spline, of the form A1, A2. Okay, so now let me introduce an example, and we'll also talk about some additional terminology associated to one of these oriented polygonal splines. So here's an example. Let's call it gamma. It's the OPS ACBBECD with an arrow over it. And here's the picture. There's A, there's C, there's B, again, of course, there's E, there's C, and there's D. Now, technically what this thing is, right? It's technically not a picture. Technically it's just a list. So on your computer's hard drive, if you ask the computer what is this, it'll say it's this. This is what it is. It's a list with the elements A, C, D, B, E, C, D in that order, and the list is enclosed in square brackets. That's what it is. Then we can picture it usefully on the plane as a kind of path consisting of these linear pieces. That's why we call it a polygonal spline. So we're starting at A, and then we go to C, so we represent that with this line segment, and notice that little arrow halfway, roughly, between them. And notice that this is not a closed arrow, it's kind of an arrow that looks like this one. Okay, so there's AC, and then CB, and then BB. Well, how are we going to visualize that? Well, we could, if we wanted to, make a little loop here just to alert us to the fact that there's actually something going on there. Right, we're going to B, and then we're repeating B. So the polygon is not really going anywhere, it's staying at B, but we're recording that fact here visually with this little loop. After we're at B, then we go to E, and then we go to C, and then we go to D. So notice that we're going back to C. That's all right, because repetitions are allowed in the list. So this polygonal path is allowed some freedom that Polygon is not. Polygon cannot do this kind of thing. Polygon cannot stay at a point repeatedly. It's not supposed to go back to where it already was unless it's the end of the loop. And also this thing's not closed. Okay, some extra terminology associated with this OPS are its oriented edges. So this thing has oriented edges, and we'll define the oriented edges of this thing to be the OPS AC, as well as CB, as well as BB, as well as BE, as well as EC, as well as CD. So we'll just go through them and we can list all of the oriented edges. Notice that BB is a legitimate oriented edge of this OPS, this oriented polygonal spline. We'll also talk about the beginning point. So we'll say B of gamma is the first point. And the end point, E of gamma, is the end point, the final point. So B of gamma and E of gamma, they will try to remember those are the beginning and the end of our splines. And we'll say that the spline is closed precisely when these two happen to be equal. So if it's the case that we get back to where we started at the end, then we'll say it's a closed spline. In other words, the begin of the spline is the same as the end of the spline. So this is a flexible kind of notation. It's perfectly captured by our list data structure. It's very useful for calculus. Very, very useful. In some ways more useful than the idea of an n-gon. So we'll leave the geometry behind a little bit and become a little bit more combinatorial or almost computer science oriented. Okay. So a very flexible and useful notion. An oriented polygonal spline. And now, the signed area of an OPS. An oriented polygonal spline has a signed area. We're going to define it now. And we're going to do that by defining it first for the simplest kinds of OPSs, the oriented edges, the things with only two elements. So if A is our usual point AB, and B is our usual point CD, then the signed area of the oriented edge, AB, with that spline kind of arrow on top of it, is, no surprise, S of AB is AD minus BC over 2. So this is the origin, and here's A, and here's B, and there's the oriented edge from here to here. Then the signed area is just AD minus BC. That's just the signed area of that triangle, OAB. It's almost the same as the signed area of an oriented side. What's the difference between an oriented edge and an oriented side? Only this, that the oriented edge is a list, while the oriented side is an O-set. The sides have to have distinct points. Edges don't. We can have an edge of the form B to B. So that's our definition of the signed area of an oriented edge.
今の仕事っていつ作られてるんですか？編集とかされてるんですか？4月から今年の4月から社会人で、なるほど、社会人とともに状況になる。そうです。なるほど、1年目。でも研修とかってないの？そうですね。いきなり現場で。今年2425の年？まだそんなに何にかけていく？
時間がいる逆に楽しい。
社会人になって時間に余裕今、もうこのぐらいの時間に終わるんですか？7時ぐらいの。
Define the signed area of an OPS. Now we should define the signed area of a COPS, or COPS. So if delta equals A1, A2 up to AN is a COPS, a cyclic-oriented polygonal spline, then the signed area is defined as follows. The signed area is equal to, let me get it properly. I want to make that a definition. It's a definition. Okay, what is it? It's S of A1, A2, so there's the first oriented edge, plus S of A2, A3, the next oriented edge, and so on, all the way up to the last one here, which is S of AN minus 1 AN, plus, crucially, plus one more, plus the oriented edge AN to A1, its signed area as well. So if this was just an ordinary oriented polygonal spline without that arrow there, then we would have stopped the definition at this point. But because of that arrow there, we're obliged to go back to the beginning and include that last oriented edge from AN to A1, which is also in the story. So, for example, here's a simple quadrilateral, A1, A2, A3, A4. And so the signed area of this thing as a cyclic-oriented polygonal spline, A1, A2, A3, A4, with the spline double arrow, is the signed area of A1, A2, plus the signed area of A2, A3, plus the signed area of A3, A4, plus the signed area of A4, A1. And each one of those, of course, has the interpretation that we're now familiar with as that of a signed area emanating from the origin. So we've been rather fussy about definitions. There are a lot of definitions, just subtle differences perhaps, but this is part of being a pure mathematician. This is a pure mathematics course, and if you're just entering university and starting off, in your career in mathematics, it's great to be exposed to this kind of fussiness, okay? I hope you enjoy it. I hope you enjoy the precision of knowing exactly what we're talking about. Now, with the word examples and the homework questions that accompany all the videos, you get more practice at seeing the distinctions play out in specific examples. So I urge you to go through those carefully, so to solidify your understanding of these differences. Because terminology, maybe it seems as if it's relatively simple and easy to absorb, but it's easy to forget, and it's easy to not remember the notation that we used. So notation is especially important. We really like having good notation, and that's what we're aiming for in this course, choosing our notation very carefully. So there's much to learn, and I'm Norman Waldberger. Thanks for listening. I'm Norman Waldberger, and welcome to the Algebraic Calculus. In today's video, we're going to touch base with the oldest calculation in calculus that involves curves. It's a very famous result from antiquity due to Archimedes, and it's intimately associated with this beautiful curve called the parabola, which will figure very prominently in our development of calculus. And we're going to use the language and the terminology and the notation of these oriented polygonal splines that we talked about last time. Okay, so the object of interest today is the parabola, which is arguably the simplest curve after the straight line. It has the quadratic equation y equals x squared. So a pretty simple equation. And here is the very familiar graph y equals x squared, and I've plotted a few points, 1, 1, 2, 4, 3, 9, minus 1, 1, minus 2, 4, etc. This will be very familiar to students of high school. Okay, so this was studied by the Greek mathematicians, notably the great geometer Apollonius, and then also Archimedes, around 200, 250 BC. But they didn't study it in this Cartesian framework with coordinates. They studied it rather geometrically as a conic section, and we're going to talk more about conic sections more generally in a later lecture. But for us, we're looking at it from this Cartesian point of view, and the crucial thing is that this parabola has a parametrization. That means that we can systematically describe the points which lie on the parabola through this simple parametric equation, t comma t squared. So for every value of t, you plug t in there, you get a point on the parabola, and corresponding to every point on the parabola is of this form for some t. It's called a parametrization of this curve, even though we actually haven't defined what a curve is officially yet. Okay, so we're going to use this, and we're going to study this parabola. We're going to look at some very interesting questions about how to define areas associated to this parabola. work with our spline notation signed areas. So along the way, we're going to be doing some calculations in this lecture, and actually I'm going to be framing the calculations and leading a lot of the details of the development to our worked problems in the actual course proper. So there's going to be some things for you to be doing and looking at and studying aside from just these videos. Okay, so there's actually quite a few things to do in this lecture today. We're going to be quite busy. Now, I've only written down a parameterization for the curve. In practice, we actually can't get at all of the points on the curve. The parameter values are including numbers which are getting bigger and bigger and bigger and eventually beyond our computational abilities to deal with. So it's wrong for us to think that we're capturing all of the points. It's too grandiose a kind of an aspiration. But what we can do is we can aspire to getting at precise points and looking at linear approximations to the curve. That's a good first approximation to what the curve actually looks like. In fact, it's quite close to what computers do when they're graphing curves. So let's look at parabolic splines. And the simple kind of motivation is when we look at, say, something like this. We look at a few points on the curve, say A0, which is 0, 0, A1, which is 1, 1, A2, which is 2, 4, and A3, which is 3, 9. So let's just look at these 4 points. So they're all points of the form k comma k squared. We're now restricting ourselves to k being an integer value here. So these points all lie on the parabola y equals x squared, of course. And we can create a spline. We can create a spline by just joining them up with linear segments. Now this will not be the same as the curve, of course, but it will be an approximation to it. So we might want to estimate what the signed area of this OPS is. So there's the OPS, A0, A1, A2, A3. This oriented polygonal spline starts here, and then here, and then here, and then here. And we know what that means. Well, first of all, it refers to a signed area that we get by starting at this point and then at this point and going back to the origin. It's a signed area of this segment. And in terms of our definition, it's the signed area of the first oriented edge, A0, A1, and then the second one, A1, A2, and then the third one, A2, A3. And because this is not a cyclic OPS, we're not going back here. We're just looking at the sum of these three signed areas, which geometrically is going to give us exactly this shaded region that we've got here. Okay, so we know how to do this. It's quite familiar by now. Calculating signed areas of segments just means taking our fundamental definition of the signed area. So here's 0, 0, here's 1, 1. We take 0 times 1 minus 0 times 1, that's 0 minus 0 all over 2. And then the next segment, 1 times 4 minus 1 times 2, so that's 4 minus 2 all over 2. And the next segment, 2 times 9 minus 4 times 3 all over 2. And we get a total of 0 plus 1 plus 3 for a total of 4. All right, that's very nice. So we've got the signed area of this OPS, which is a kind of integral approximation to a part of the curve y equals x squared. Now, as we go through the course, we like to make specific computations, but we also want to look towards a little bit more general computations that shed a little bit more light on the pattern of what's going on. And let me illustrate that here by replacing that specific spline that we just looked at with a more general spline, but still really in the same direction. So instead of just going up from A0 up to A3, let's go from A0 up to AN, where n is some positive integer, natural number, but it's not specified which one exactly. So we're still talking about things with form a sub k squared, where k is, in this case, a positive integer. And we'll look at the spline A0, A1 up to AN. A0, A1, A2, A3, A4, up to AN, whatever AN is. And the one just before AN will be AN minus 1. Okay, so what's the signed area of such an OPS? Well, it's going to be the sum of the signed areas of all its oriented edges. So S of A0, A1, and then S of A1, A2, plus S of A2, A3, etc., all included there, till the final one, S of AN minus 1, AN. It's the sum of all the oriented edges of this thing. So now we have to get at what does a typical oriented edge look like and what's its signed area. So let's look at, rather than a specific value, let's look at a general value. Let's look at a sub k minus 1, which is k minus 1 and k minus 1 squared, together with a sub k, which is k squared. So we're looking at it now to the point of you having this variable index k instead of a specific index. So what is the signed area of this oriented edge? Well, we can do the same thing. It's k minus 1 times k squared minus k minus 1 squared times k, all divided by 2. Okay, so when we look at this, there's a k minus 1 that's common, and there's a k that's common. So we can pull that out, and there's a 2 on the denominator that's also common. And what would we have left if we pulled out those common factors? Here there would be a k left over, and here there would be a k minus 1 left over, and we have to take a difference of those. So k minus k minus 1, that's just 1. So that doesn't appear. So this thing simplifies to just k minus 1 times k over 2. And this is a very special kind of number. It's a binomial coefficient, k choose 2, and it's a triangular number. So the signed area of one of our little oriented edges in this pattern of points lying on our quadratic curve with integral values, these numbers are triangular numbers that we're getting. So here's our formula for triangular numbers, n choose 2, which is n minus 1 times n over 2. And here are the values of these things. So here's the values of n from 1 to 10, and here are the corresponding triangular numbers n choose 2. So when n is 1, we get 0, when n is 2, we get 1, and then we get 3, and then 6, and then 10, 15, 21, 28, 36, and 45, and so on. And we call triangular numbers for an obvious reason. If you look at this little diagram here, this is the case when n equals 5, there's 10 of them all together. And you can see 10 balls or circles arranged in a triangular kind of pattern, 4 on the bottom, and then 3 on top of those, and then 2 on top of those, and then 1 at the very top. 1 plus 2 plus 3 plus 4. It's another way of thinking about what this triangular number is. And that total is 10. And notice also that to go from one of these entries to the next one, we can do it relatively simply. To get the 15, we just take 10 plus 5. That gives us the 15. And to get the 21, we're just adding 6 to the 15. And then here we add 7 to the 21, and so on. This is a very famous sequence going back to the ancient Greeks, who were very interested in the geometry of these numbers. They thought they were very pleasant numbers, which they are. And in Sloane's online encyclopedia,